Let's go ahead and derive the centripetal force equations. I have most of it written out here already, and we'll highlight as we go along. To start with, here is a mass m that is moving in a circle that is of radius r. And I've drawn the mass m at 2 times. And the velocity vector of mass m initially is this velocity vector, and at some short time later, delta t later, this is its velocity. The magnitude of the velocity is not changing, but the direction clearly is. And the direction of the ball, or the direction of the ball's velocity, turns by an angle theta in the time delta t. The distance along the curved path of the circle that the ball has moved is v delta t, velocity or speed times the time. Now here we have a triangle. Now this side here is curved. It's the curved edge of the path of the ball, the circle. However, if delta t is a very short time, then the curvature of that edge is really irrelevant. And actually, if you take delta t from moment to moment, that is, delta t is an extremely short time, then in that limit of short delta t, the fact that is curved is really not important. Now, what I've done over here is I've drawn a triangle with VI. So imagine I just pick up VI and I put it right here. And then I pick up VF and I drag it and I put it right there, tail to tail. And those are the two velocity vectors, the initial and the final velocity vector for the mass m. And here I've drawn delta v. That is, delta v, by definition of delta anything, is it's the final minus the initial. And so if we rearrange that, that is, we bring the vi over to the other side, we have that the final velocity is the initial velocity plus delta v. Well, if we look at our vector diagram, the way we normally add vectors is we add them head to tail. And so we have the initial velocity plus delta v, and vf is the resultant of vi plus delta v. And that's how we add vectors when we draw them. Now, in our diagram, notice that we have the same theta between the two lines here forming the long sides of our triangles. And so these two triangles are similar triangles. I have quotes here around the word triangle because of this curved edge. But again, if delta t is very short, then the curvature there is just not important. And so we have two triangles that are similar. And what that means is that the ratio of corresponding sides in the two triangles is the same. So in other words, if I take delta v divided by v, that's this ratio right here, then that ratio is the same thing as v delta t, the distance traveled by the ball, divided by r. So we have the far side divided by one of the sides relative to theta, the far side divided by the side, and the far side divided by the side, the corresponding sides. And that is the angle theta measured in radians. Now, we don't really care about what theta is. What we care about is that these two ratios are equal to each other. So now we can apply the equation for acceleration. Acceleration, by definition, is the rate of change of the velocity, delta v over delta t. And so coming up here to this equation, we can bring the delta t over to the right-hand side, delta v over delta t, and we have to get rid of this v, multiply both sides by the v, brings the v over to the other side. So we have delta v over delta t is v squared over r. And that is the acceleration. That's our definition of what we mean by the word acceleration. Only in this case, we're going to call it the centripetal acceleration. It's not that the speed of the mass is changing, but its direction is. And lastly, we can multiply the acceleration by the mass to get a force. F equals ma. So take m times the acceleration, you get a force. And in this case, it's the centripetal force, mv squared over r. Now we're going to derive a slightly different version of this using different variables, because when you have a string and you whirl a ball around on a string, you don't really have a good sense of how fast the ball is moving, but you do have a good sense of the period, that is, how much time it takes for it to go around. So let's introduce two variables here. One is capital T, which is what we call the period. By definition, it is the time for the mass to go around the circle once. And so time is distance over speed. And so the distance to go around the circle is the circumference of the circle, 2 pi r. And so the distance, 2 pi r divided by v, gives you the period. Now, the other variable we're going to introduce here is f, the frequency. Frequency is the inverse of the period, 1 over t. So if you think about t, the period, as the number of seconds it takes for one revolution, then the inverse of that is the number of revolutions per second. And you can use different time units. One that gets used a lot is revolutions per minute, or what most people call RPM. So, but if you measure the period in seconds, the frequency would be revolutions per second. If you measure the period in minutes, then the inverse of the period, that is the frequency, would be revolutions per minute. If you measure the period in days, then the inverse of the period, the frequency, would be revolutions per day. So let's use these two new variables, and v, the speed, 2 pi r over the period. So another way to write that is 2 pi r times f, 2 pi r times the frequency. And lastly, what we are going to do here, just to finish this off, is we're going to take our equation for the velocity, 2 pi r over t. We're going to plug that in there for the v in our mv squared over r. So we have m times 2 pi r over t squared over r. Four pi squared mr over t squared is our centripetal force, or if we want to write it, 4 pi squared mr f squared is another way of writing it. So in terms of our final equations, we have the centripetal force, mv squared over r, and we also have 4 pi squared mr over t squared And we can also write this way. Wouldn't necessarily memorize all of these. What I would suggest memorizing is the centripetal force is mv squared over r, and that the period is 2 pi r over v. And if you ever need this equation down here, well, you can always rederive it.